Hi ladies and gents, we are taking a look on page H10, number 4, and we're talking about the cigarette example but from a p-value approach. Let's just review for a couple of minutes what we did last time here. We said that we've got this thing called the classical approach, and so here's the problem, the cigarette example right here, that mu is less than or equal to 1.6 against the alternative that mu is greater than 1.6. In the classical approach, what we do is we find a critical value, in this case it was 1.645, associated with an alpha, and we assumed an alpha of 5%. And then we said, well, if our T star turns out to be greater than that 1.645, we would reject HO. By the way, I know down here it says Z star, but we had 143 degrees of freedom, so the T distribution and the Z distribution are virtually the same at that point. In the p-value approach, though, what we do is we say, instead, let's figure out what the T star value is, and then find the area associated with that. If that area is less than an alpha of 5%, then we reject HO. So that's called the p-value approach, and so let's actually do that. The thing to remember about the p-value approach is that there's nothing new there. That's actually how we calculated probabilities right through unit E. And it got it started in unit N, actually. Let's take a look at how we would do this. Step number 1, let's go back here and just take a look at the steps again. So step number 1 is our HO and our HA right here. And then we go to our formula sheet, and then we have step number 3 is going to be a little bit different here. It's our decision rule. Then we're going to do our computation, and then we're going to do our conclusion. So let's do that using the p-value approach. So the cigarette example here, step number 1 is we had that mu is less than or equal to 1.6. That's the standard. No more than 101.6 milligrams of nicotine. That's the standard they need to meet. HA is that mu is greater than 1.6. There's nothing here that says anything about what the level of alpha is, so we will assume an alpha equal to 0.05. Step number 2 is we go to the flow chart, and I'm not going to do that. We ended up with formula number 3. And so that is T star is equal to X bar minus mu naught over S divided by the square root of N. You can go back and take a look at the last video. Basically, we found out it doesn't say anything about normality, but because N was 144, the central limit theorem kicks in. Sigma was not given, so we use a T distribution. So T star, you computed T, is equal to X bar minus mu naught over S divided by the square root of N. Now, if this were the classical approach, what we would do that next is to find out what is the critical Z value. And that would give us our decision rule. Here, we just simply say the stats mantra. If the p-value is less than 0.05, which is our assumed alpha, then you reject HO. That's all it is. It's just a statement like that. Step number 4 is where we take the sample now, we stick the numbers in. So we got 1.7 minus 1.6 over 0.5 over the square root of 144, and that comes to 2.4. Step number 5 here then is we take a look at, well, where does that 2.4 actually land in a t-table, what we do is we take a look at our degrees of freedom, which is 143, so we're going to go to the Z row. We're going to go across here until we find 2.4, which is right in here. And we go up here and we find that the p-value will be somewhere between 0.5% and 1%. Let's go back and write that. So we've got the p-value, the area associated with that, is somewhere between 0.5% and 1%. Does that look familiar? Yeah, that was the first way that we solved this problem, right at the beginning of this particular unit. So that was actually the p-value approach. But what we have here is that that is less than 5%, right? So the p-value, this is the p-value, somewhere between 0.5% and 1%. It's less than your alpha of 5%, and therefore you reject HO. And that's our conclusion. We reject HO in favor of HA. Let's work through another problem here. And then I'm going to leave you number 6 for homework. So let's take a look at this one here. In fact, I'm going to do this as both a p-value approach and a classical approach. I'm going to put them side by side here. So let's do the classical approach here. And let's do the p-value approach here. All right, let's take a look at what we've got here. Let's look at the problem first. The mean breaking strength of a type of steel has been established from long use to be 20 kilograms. With a standard deviation, and that's, by the way, a mu value, and a standard deviation of 2.8. So that's a sigma, right? This was the mean breaking strength, or the average breaking strength. Doesn't say anything about a sample. This is talking about a population value. So mu is equal to 20, sigma is equal to 2.8. A research engineer claims to have developed a superior wire at about the same price. And so they take a sample of 100 pieces. Now we're talking the sample, so this is a little n. And we end up with the mean breaking strength of the sample turns out to be x bar is 21. Would you conclude that the research engineer's claim is correct? Whenever we're talking about a claim, it's a hypothesis test. And then, of course, when you see a statement that says use of both a classical and a p-value approach, you know that that's a hypothesis test as well. But this is a claim being made. So what's the HO in this particular case? Step number 1. HO is that the mu is, well, let's start with just the equal, and then we can change that to less than or equal to or greater than or equal to. The standard is 20. So the mean breaking strength of a type of steel has been established from long use to be 20. Remember, the HO is always the status quo, right? The traditional. Now, the HA is talking about, is the new wire better? A superior breaking strength would mean that it has a greater breaking strength. So a superior wire means that it has a greater breaking strength. So the alternative hypothesis is that mu is greater than 20. Now, it's okay to actually leave the null hypothesis as mu is equal to 20. What I usually do is make this less than or equal to 20, because what we're really doing is we're trying to disprove the null hypothesis, we're trying to prove that the new wire is better. And so we're only interested if the mean is greater than 20. If it's less than 20, well, that just supports the old wire, right? So here's your hypothesis that mu is less than or equal to 20 against the alternative that mu is greater than 20, a superior wire. And the p-value is exactly the same. So step number one is the same. HO, mu is less than or equal to 20. HA, mu is greater than or equal to 20. We're going to assume an alpha here of 5% because it isn't specified here. So same thing here. Assume an alpha of 0.05. Okay, step number two is where you go to the formula sheet, which is just the flow chart here. And so the flow chart here then asks us, okay, let's go through this. Does it say anything about the population being normal? And if you remember the problem here, the answer was no, I don't think so. Don't remember. Let's see. Mean breaking strength is being established to be 20, yada, yada, yada. We take a sample of 100. I don't see anything in there about it talking about normality. Okay, but your sample size, your sample size is 100. So that's quite large there. So the answer to, at this particular point then, is no. Is n at least 30? Yeah, n is equal to 100. So the central limit theorem kicks in. Is sigma known? Yes, it is. So that means that we're going to be using a Z distribution. Is big N known? No. So we're going to be using formula number one. Formula number one is just a regular Z star formula, which we were introduced to at the beginning of Unit E. Okay, let me just back all those things up here so we don't have them. There we go. So we're going to use formula number formula number one, which is a Z star formula. So this is formula number one. That Z star, that's how I draw my Zs. You can do it however you want, is x bar minus mu naught, or hypothesized mu, over sigma over the root of n. Step number two is the same in the p-value approach. Step three is where there's a deviation. So in step number three, we are taking a look then at the critical region, the critical value, and the decision rule that goes with that. So let's take a look at a normal table here. So this is Z. And take a look at the sign of the alternative hypothesis. It points up. And so we're going to put the whole alpha in the upper tail. Now, I'm not going to go back to a Z table. You can find that. It turns out that that value, is 1.645. You can go to a Z table, or you can go under the 5% column to the bottom of a T table, and you'll find 1.645 there. So your decision rule then is if the Z star value is greater than positive 1.645, then you reject HO. By the way, on an exam, you could just simply write that statement. You don't have to draw the picture. Either the picture works or the statement works. They both say the same thing. And if you're doing this on a computer, on an exam, it's hard to draw this thing out, so you can just simply put the statement down. Step number three over here in the p-value approach is just simply the statement. It's the stats mantra. If the p-value is less than 5%, which was our assumed alpha, then you reject HO. Step number 4 is where we actually go and we calculate. We take the sample and we do the calculation here. So we're going to go and grab these numbers here and stick them into the formula here. So Z star is equal to X bar, which was 21, minus mu naught, which is 20, over, what was the standard deviation? That was the sigma of 2.8 over the square root of 100. That turns out to be 3.57. That's way out in the tail. Step number 4 over here is the same. So Z star turns out to be 3.57. And so what we do is we're going to find 3.57. Hey, just to back up here, that critical value of 1.645 is right in here. Right? That would be 5% in the upper tail, which would be 45% from that point down to the middle. So that's 1.64 or 1.65, 1.645. We're looking for 3.57. And so we go down here and actually this thing actually ends at 3.49. So it's even further in the tail than this. 0.4998, it's the 0.5 minus that. So it's going to be less than 0.0002. So what we have here is that this is 0.4998. And so this here is going to be 0.0002. And that's our p-value. Let's go back to where we were. So what we've got here then is, in the classical approach, this is really easy to do. We say, here's 3.57. That is in the critical region. So we say 3.57 is greater than 1.645, which is the critical value. Therefore, we're going to reject HO. In the p-value approach, what we do is we go to the table, and we found that that probability there, that probability of Z being greater than 3.57 is something about 0.0002. It's actually less than that. Let me just draw a picture of that, which you wouldn't necessarily have to do this, but this is what we found here. Here's a Z distribution, and we found 3.57 here. And this area here was 0.4998. So that p-value then is 0.0002. It's actually less than that, because that was the last number on the table. It's actually less than that. So it's about 0.0002. So what we have here then is the 0.0002 is less than your alpha 5%, therefore reject HO. So taking a look at these two together here, steps 1, 2, and 4 are exactly the same. But in each case, whether it's the classical or the p-value approach, you go to the table. So in the classical approach, you went to the table at the beginning here to find the critical value. The critical value was 1.645. And then when you figure out the computed value from step 4 of 3.57, you just compare those two. In the p-value approach, you don't go to the table right away. You figure out the 3.57, and then you go to the table. And you find the area associated with that, and that's the p-value, and you just simply compare it to the alpha. So either way, you go into the table, they come up with the same results there. Last thing I want to show you here is just if this were Excel, how would you get that 1.645? So the critical value, I'm just going to call it the CV, the critical value would be found by this formula here, this function. It's a norm.s.dist, and then 0.95. And then I think you have to put in true. So that's what it looks like. Over here, the p-value approach, sorry, made a mistake there. It's not a dist function, it's an inverse function. Like so. And I think you just put in 0.95. For the p-value, you use a dist function. So this right here, let me do it right down here, would be a, let's see, we're going from some point up. So it would be 1 minus norm.s.dist, 3.57 true. So that's what that would look like. Okay. So the inverse functions are used to find critical values. The dist functions are used to find p-values. All right, I want to leave you this problem here for homework. Just a hint here is that this is a two-sided test.